And now for the question of how much of the variation in the y variable do we actually explain by using the information in our explanatory variables, the x variables. So, and in the simple regression model, we have the r squared, which is the small r squared, because r is for the Greek letter rho, which stands for the correlation. From the simple regression model, r squared is just the correlation between x and y squared. Okay, and the r squared, the capital R squared, which we use in multiple regression model, measures the fraction of variation in y explained by the explanatory variables. It's actually over and above only using y bar, the average of y, as forecast. Okay, so for example, what is the r squared in Starbucks? And the r squared in Starbucks equals 0.59, which tells us that our x variables median income and the number of competitors they explain 59% of the variation in y. Okay, and another number which is more used than the r squared is the adjusted r squared, and it's denoted r squared with a bar over. I removed this bar this bar instead of that bar, so down here you should not have a bar. Okay, so denoted r squared bar, or r bar squared, just for the sample size and model size k. So for example, if you have a lot of x variables, then you have a more complex model. Okay, and if you have a lot of n, which is a lot of observations, you are more and more certain about your model. Okay, but if you want to look at how much how much of the variance in y that the x's can explain, then if you only use r squared, then for each x variable you add to the model, and the more complex the model is, the higher the r squared. And this is true even if the x variable is not relevant. So you can say that the r squared is non-decreasing in k, which is the number of variables. So if you want a really high r squared, then you just add on variables and just add data into the model, but the model becomes virtually useless, okay? Because you're adding irrelevant variables. So to check if you're adding something useful or not, then you can use the adjusted r squared, because it's adjusted both for the sample size and the model complexity. Okay, so and the way you or the computer calculates the r adjusted r squared is the adjusted r squared equals to 1 minus r squared times the n minus 1 divided by n minus k minus 1. Okay, and so this is what you would normally use. Okay, and this is often called root MSE. So the measures of explanatory power is the r squared, the adjusted r squared, and the standard deviation of the residuals. Okay, and the standard deviation of the residuals, they are calculated just as in the simple regression model. So they are calculated exactly in the same manner, and they are not adjusted like the r squared. Okay, so these standard deviations of the residuals, they can be used to kind of make prediction intervals. Okay, make prediction intervals. So this is y bar, and this is like the 95% prediction interval. Okay, and to make the prediction interval, we saw that in the simple regression model, you could approximate the 95% prediction interval by just forming a band of around y hat by adding 2 times the standard deviation of the errors and subtracting 2 times the standard deviation of the errors, or the RMSE, root mean squared error. But it's important not to make prediction intervals outside the range for which we have data. So if you have data in this range of y and one of the x's, and suddenly you want a prediction for this point, this circle, then you are extrapolating. And if you let the computer deal with the prediction interval, then you would get a better estimate of the prediction interval, because it takes care of the extrapolation. So for example, this is your band, and as you are extrapolating, the band gets wider, okay, compared to where you have data. The band is oh, sorry, they should not be, they should be vertical, okay, they should be vertical. So the band, almost vertical, okay, the band is much wider if you extrapolate, okay. So it's better to let program calculate. Okay, so for our example, what is the predicted sales per square foot at a location with median household income of 700,000 kroners and 3 competitors? What is the 95% prediction interval around it? Okay, so what is the predicted sales per square foot? Okay, so we have the square meter sales per square meter, and that would be the intercept of 6,496. I don't have it in my head, so I'm looking at my cheat sheet, plus the slope 85.75 times the median income, plus or minus 2,601.10 times the number of competitors. So that's our fitted line, and if we just add some numbers, we get 6,496.95 plus 85.75, and this is in kroners per thousand median income. So we times 700 plus minus, of course, minus 2,601.10 times 3 competitors, okay, and that would be equal to 58,000. Let's see, 718.65. So that's the predicted sales per square meter, and the 95% interval, 95% prediction interval equals the sales per square meter estimated plus minus 2 times the standard deviation of the errors, and this is 58,718.65 plus minus 2 times, and the standard error of standard deviation of the errors, they are from the table of results here. It's the same as the root MSE. It's 7,322.8. Let's see where we have it. It's 7,322.8, which gives us a range of 44,000 and 73.05 to 73,000 364.25. Okay. So if someone gave you the information that in this location the median income is 700,000 kroners, there are 3 competitors, what is your best guess of our sales? And you would say that, well, my best guess of our sales, my point forecast is 58,718 kroners per square meter, but I'm 95% certain that the true sales will be somewhere in the range of 44,000 until 73,000. Okay? And what we have to look at is the conditions, and to say anything from or to make any sense of the model, we have to make sure that some conditions are met. And luckily, the conditions in the multiple regression model is basically the same as the conditions we have to meet in the simple regression model. So the residuals, they have to be independent, which means no pattern. Okay. Or in time series, data, no autocorrelation. And that we test by the Durbin-Watson statistic. Okay, and of course they have to have equal variance. So around the one of the x's, if we plot the y, holding other x's constant, the variance of the residuals should be equal. So there should be no pattern here. So the range or the standard deviation of the variance should not change because x changes, or any of the x's changes. Okay, so and lastly, the errors should follow a normal distribution, and this helps us to create prediction intervals. So if these conditions are met, then our prediction intervals are more correct. Okay, are correct. So, and what we can do is that we plot, of course, we plot the residuals against the predicted values of y, as well against every single x variable. Okay. So for example, for the simple regression model, we had a y and an x, and we could plot the fitted line, and we could get the residuals. We could plot the residuals against, sorry, and yep, and then as the okay, that was not the errors. The errors, they are centered at 0. Okay, so let's make 0 here, and we take this away. Sorry for the disturbance, but if we have the errors here, and we can calculate the residuals, right? So and that would be along the x-axis. So for example, with the simple regression model, we can easily fit the line, okay, and plot the line, I mean. But with the sample regression model in a multiple regression model, then it's difficult to okay, let's see, so difficult to plot, because here you see that in the simple regression model with one x variable, you can easily plot y versus x in 2 dimensions. Whereas if you want to plot the multiple regression model, you need to plot it in k+1 dimensions, which is quite difficult. So it's difficult to plot, but it's easy to calculate the expected y given let's see, given coefficient and x values. Okay, so if you have the intercept and slopes, then it's easy to calculate the y hat from the model. And if you have the data, the y, and for example x1 and you have x2, then you can use your model and just plug in x1 and x2. Okay, you plug in x1, x2, and then you can just create the y hat, right? And if you have the y hat and in addition you have the y, then you can create the error. Okay, the residual. So then it's quite easy to kind of plot these variables against each other. Okay. So, for example, from the Starbucks case, we have the e's here, and the residuals should be centered at 0. Okay, and you have the fitted values, the y hats, and if you look at the scatter plot, then there is no obvious pattern. Okay, so here you just take the regress sales on median income and number of competitors. Okay, and then you predict the y hat, and then you predict the error. Okay, the residuals, and then you just plot a two-way scatter of E and Y hat. Okay. And you here you see no pattern. The variance of the residual is not dependent on the y variable. So this looks good. And of course you plot the residuals on the x variables as well. And this is the residual. It's centered at 0, and it's plotted against the median income, and it's a scatter plot. It looks random, which is good, and the same can be said about the errors against the number of competitors. And lastly, you just look at the histogram of the residuals and look for normality. So the histogram should kind of fit the symmetrical normal distribution. And remember that we have n equals 65, which is not a lot. So this deviation from normality might be because of chance, but you have one hump, kind of one peak, which is classical for the normal distribution. So we don't really see any problems here. Okay, so that's it for this time. Next is the F statistic.